Thank you so much. Thank you for coming. Thank you for inviting me and organizing. Let me reiterate that if you want to interrupt me, I didn't know who the audience would be, so I have not quite taken the time to add things on slides that explain things at a level that you might want to hear, but I'd be happy to use the board. And I'd be happy for you to interrupt me whenever you have clarifying questions. And then, yes, so I am working on this new method. We have this exciting application, but my collaborators and I are not political scientists. We would like to work more with political scientists, and so if this all sounds interesting to you, whether for actual US elections or other elections, or there are many other non-election applications, please come talk to me. I would love for new collaborations. That would be great. Okay, so what I'm talking about today started using data from the 2012 US election, and then we updated it using the data from the 2016 election right after the election, and then we sort of put it aside because working on it furiously the night of the election and the days afterwards sort of gave us a bit of PTSD, and so I think we're maybe ready to come back to it. There are very important, interesting questions, which I'm sure you have many that I have not thought of. And so we'll get there, but let me tell you about this method. So what is the classic ecological inference problem? It has different names. So now let me think. What do people in political science call it? People have heard of ecological inference? People have heard of Simpson's paradox? Ecological fallacy, yes, absolutely. Sorry, that's the ecological paradox. Simpson's paradox, modifiable areal unit problem. Maybe that's more like a spatial econometrics name. It has a bunch of names because people come across it all the time. So here is the voting version of it, but I can tell you if you're interested how you can translate this into the medical domain where it's Simpson's paradox. So we've got a bunch of districts in the United States, colored red and blue, just so you're thinking about electoral outcomes. And what do we have? Well, often we know somehow from the voter rolls, a certain number of people voted. Well, that's from the electoral outcome data. So that's here in this 2x2 table. We've got 2,200 votes in some district, just one of these little polygons. We've got 2,200 Democrats, 1,300 Republicans. And then somehow we also know the number of blacks and whites who voted. And what we would like to infer, and so this is important for legal reasons in the United States related to the Voting Rights Act, we would like to infer the inner entries, the inner cells in this 2x2 matrix. But this is an undetermined problem, right? We know some bounds. The number here plus the number here has to add up to 2,000. The number here plus the number here has to add up to 2,200. And so you can think like, okay, I'm going to write down some inequalities. A plus B equals 1,500, or less than or equal to 1,500. And I'm going to write those down. And so this is the so-called method of bounds, dating back to the 50s. I'm going to do that for each district. And that's going to do something helping me a little bit sort of say, okay, these inner entries that we don't know exactly, we know that they're bounded somehow. That approach is not wrong, but it's not statistical in any way, right? There's no regression that we're running. We're not looking for an association between any variables. And although you might get an upper and lower bound from that method, you're not going to get anything like a confidence interval out of it. So a different approach, also invented in the 50s, things called Goodman's method, says let's think about each of these districts as an observation. So I've got the fraction of the vote outcome, so maybe 53% for the Democrat. I've got the fraction of voters who are black, 30%, and then I'm going to do a regression of the variable that I want, Y, outcome, voting outcome, on the variable that I am using to predict, the race. And so you might think you should set that up as a logistic regression for, I think, historical reasons. Actually, it predates logistic regression. They set it up as linear regression, regressing an outcome like 0.6 on some real valued variable, 0.4. So this is vote, and this is racial breakdown. And this gives preposterous results. This gives things that are greater than 100% or less than 0%. And I will show you that here. So, oh, there are the years, great. So Robinson, 1950, talked about the ecological fallacy. Duncan and Davis gave the method of bounds, which I described. Goodman's method is a few years later. So when does logistic regression get invented? I think it's the 60s by Cox. And then there's some newer stuff. But look at this. This is statement of Gordon G. Henderson, presented as part of an exhibit in U.S. federal court. All Ohio State House districts where an African-American Democrat ran against a white Republican, 1986 to 1990. And then what do they estimate in each of these districts? Percent of blacks voting for the Democratic candidate. And this is, again, based on the sort of statistical-ish method, Goodman's method, 100.06%, 111.05%, which makes no sense. On its face, that's preposterous. This was entered in the court record, and the court still, I think, says that you have to use these classical methods. You can't use newfangled stuff that might give numbers that are possible. I've run these sorts of methods on the data that I'm going to show you, and I found things that were like negative percents, whatever that means. So there is a real problem here. And you might think like, oh, these are just kooky old school methods. The newer stuff that's out there, okay, so David Friedman, famous late statistician from Berkeley, has his neighborhood method. And no one could ever quite pin him down about whether this method was supposed to be a real method that he thought people should use. It has very, very strict assumptions built into it. Or if it was just supposed to be something criticizing other people's stuff. And so Gary King had something else, which was a Bayesian model that had built into it the method of bounds in terms of bounding things. It had a statistical method in terms of doing a regression. And Friedman said, well, there's no way to check any of those assumptions, right? It's a model, so you build in assumptions. And so it doesn't make any sense. And then there's some other subsequent work, but it's really, in some sense, remains an impossible open problem. I don't want to call it a fallacy or a paradox. The fallacy or the paradox is when you conclude from purely ecological correlations, meaning at the group level, something about the individual. And that's Simpson's paradox, if you've heard of that, that says, oh, I've got a correlation about people, now I'm going to apply it to subgroups, and I'm going to be surprised when the sign of the correlation changes. That shouldn't be a surprise. There's nothing causal when we're talking about these sorts of correlations, and that is indeed the paradox. So, what do I have to offer? Well, we often have, in many of these settings, not the historical ones necessarily, but right now, any particular case that you might think of, we often have unlabeled individual level data. And so please do ask me clarifying questions if I'm using like machine learning jargon, which has a different name in statistics or political science. So unlabeled labels. Anyone know why it keeps flashing like that? Nothing I'm doing. Okay. By labels, I simply mean in a regression setting, I've got covariates X, and I've got Y that I want to predict, the outcome variable. In machine learning, we just call those labels. If we have images in machine learning, they might be labeled as cats and dogs. So everyone okay with that language? So we often have individual level data, microdata. That's language that you should be okay with, right? Everyone in statistics is confused when I talk about microdata. They're like, is it really small? What happened to it? So we've got microdata. And what is that microdata? Well, it usually, in what I'm doing, comes from the US Census, but it might come from some other survey where you have individuals. But we don't have the outcome we care about. This is missing. Why is that? Well, with the election data, we know from the US Census, which runs a ongoing microdata sample, 5% sample of the United States population, we have individual rows, but we don't know who those people voted for. Indeed, we don't know if those people voted. So that's a big data set. That's millions, 10 million rows, something like that. And then separately, not linked to it, we have outcome data. So in some sense, I am telling you that I can solve the original problem, but in some sense, I've made the problem easier for myself, sort of. Now I have 10 million rows to do something with. None of them are actually connected to the outcomes I care about. But that's the idea. And so this has been exploited a lot in machine learning in settings that may or may not be of interest to you, but just these are the names and some citations for people who've already worked in the setting of, I have a lot of observations, and I don't know the labels. The learning from label proportions says, so I made them red and black, but I don't actually know for any of them what they are, but I know the fraction 2/5 are black. Distribution regression I'm going to tell you about. This has connections with data privacy, as you might imagine. If we can de-anonymize in some way, then that would be a problem. And so there's questions about what are the limits of this. And then I mentioned this before, there are some Bayesian approaches that do actually exploit individual level data. And so I don't want to say that I'm the only person who's worked in this area. What we are offering is a new non-parametric method and a new scalable method. Whether or not you care about those things, I'll try to convince you that those are things to care about. Okay, so here's the setup. So we saw that map already. I think that's from 2012. Voting results look something like 52% or 48% in terms of the outcome, or they look like counts, right? That's simply one way of representing what could be 100 votes for 52 votes for Obama out of 100 people who voted. And foreshadowing for later, what about the people who didn't vote? Okay. I already mentioned this. We have the American Community Survey, which is amazing. You can download. It's gigabytes of data. You can download online without even registering this ongoing survey. They change the geography every 10 years to keep up with the US Census, with the decennial census, which is a little bit annoying, especially when you want to use data that's from around 2010. And what do we want to do? So we want to solve this problem of ecological inference, by which I mean for any particular demographic group that you care about, in any particular place, so I'm going to do everything in a spatially varying way, can I predict the vote outcome among that group? So among women who live in Texas, what was the support for Obama? That's a question that I want to be able to answer. And that's something that you can get from exit polls, that you can get from other sources of surveys, that you can get from opinion polls taken right before the election, which are sometimes accurate, sometimes not. But what if I wanted to say, okay, I want to know about women over the age of 30 employed in higher education. That's not something where we're ever going to have a large enough sample in a survey to answer that question with any confidence. I claim that our methods make it possible to try to answer that question and give uncertainty intervals such that you can say, well, that's not a useful thing. You know, the answer is 52 plus or minus 19%, or maybe not. And so that's, we'll get there and you'll see the uncertainty intervals at the end. So everyone with me on the setup? Feel free to ask clarifying questions now. Okay, so immediately we have a problem. The electoral data, for example, in Florida, there's 67 counties. At some point you can get finer grained data. And so we were working with what we had readily available, but sort of as time goes on, there are people who are going around to every single tiny precinct in the United States and getting that into a database. And so probably now we could go back to 2012 and get finer grained data. Is it useful? Okay, well, we've got the 67 counties. And then we have census data for these not quite overlapping, but not terribly different public use microdata areas, PUMAs. And so there's 127 of them in Florida. And so then we do this merging thing, which at least in the US, nothing ever crosses a state border. So merging for Florida resulted in 37 electoral regions. And that's the sample size that we have for Florida. I mean, we're going to do it over the whole country. And so our sample size is using the newest data, something like 950. Using the data pre-2010, it was something like 850. So not a huge sample size, especially because I told you that we could deal with millions of individuals, but those millions of individuals end up in these 850 regions. And so maybe immediately you're wondering, haven't I lost a lot of information? Well, I'll get there. Okay, so what is ground truth? I put this in quote. I think it needs even more quotes now that I've learned more about how these exit polls work. In the United States in 2012, large media organizations together were only able to afford to pay Edison Research, polling firm, to do exit polls in 18 states and nationally representative. And that means, to do them at such a scale that they could make claims that were state representative in 18 states. So there are people who are polled all over the country, and using that data, they can give a national exit poll with the margin of error. And there are 18 states where they make estimates. But how do they do it, right? So an exit poll is literally a poll where they stand at the exit of the place in which people are voting, polling places. And as people come out, they go up to them with a clipboard and they ask them a series of questions. There's, of course, differential non-response. Everyone knows that there's differential non-response. How do they try to adjust for that? Well, if you're walking towards me and you walk away, then I try to guess your age and sex, and I write that down. And then later on, they try to adjust for that. Do they adjust for that in a way that works? Certainly not on election night, when these things are being used in order to make calls for some of these states and to drive coverage. Later on, they end up adjusting things based on the data that becomes available later on, which is the data from voter rolls. And so eventually, and sorry, just from the exit polls, right? I said exit polls. They end up adjusting the exit polls to match the actual election outcome because they want it to not be ridiculous in terms of people looking back on it. So there's many questions there. None of it is sub-state representative, and of course we're missing more than half of the states. This is the US, just to step back for a second. People are very interested in Brexit, rightfully. There was, as far as I'm aware, please tell me if you know of another data set, there was one exit poll done right after Brexit, Lord Ashcroft. I don't think that his company has the best reputation, and that was it. So anytime you read about Brexit or talk to Professor Tilley, who wrote the book, or wrote the addendum in his book about it, there isn't great data to go on, right? The data that they have is, in some sense, ecological data. They say these are the regions that voted for Brexit, and then from that they can make inferences, but that's not enough, in my opinion. Okay, anything else to say about exit polls? Yeah, so the other thing to say is that now, a few months later, there's things like the American National Elections Survey that have been in the field that I think results will be available soon. There's voter files, but voter files only say name, address, probably sex and age are available or in there, and whether or not you voted, right? There's no record of who you voted for, that's secret. And so often that's enough if you're later on doing something based on that data, but often you want to infer ethnicity or race. You want to infer education, which was a huge source of variation that hadn't been in previous elections, and those things are not in the voter file. Maybe they're inferable from it, but it's hard, right? So in the US, first generation Latino immigrants have names that are identifiable as Latino, and there are good ways of inferring that. But if you go back to second, third, fourth generation intermarriage and other reasons, names are not distinguishable from Caucasians in the US with any accuracy. Okay, so again, that was all set up. Now I'm going to tell you about the first paper that we wrote on the 2012 data, and then how we refine things for 2016. So the insight is that we can use this individual level data, and specifically there is this new exciting method in machine learning for problems in which you have groups of observations, and generically you have labels. What's the term that I should be using? Outcome variables, y. So here's group 1, and here's outcome label y1. And so this could be real, or it could be a percentage, like 52%, or it could be, this is what's going to be useful for us, binomial counts, like 25 votes for the Democrat out of 60 votes total. And that's the outcome variable. And then what are these input variables? What are the covariates? Well, each of these represents some individual whose label we don't know, but generically, each of these is just some sample from some distribution. And so each of these is just something that's, just think of it as a real valued vector. So maybe this one is a 3-dimensional vector, 0.3, 10, -1. And this one is a 3-dimensional vector, 0 to -5. So if this was standard regression, right, I would have labels for all of these. I would have y for each one of these, and then I could just do a regression of y on x. But I can't do that here because I've got all of these unlabeled and then one label that goes with all of them. And so the reason that this machine learning method is called distribution regression is I think of each of these as its own distribution, and then I'm doing regression of a label onto a distribution. I'll show you a picture. I'm going to say that like 3 more times. So if you didn't catch it that time, I'm going to say it again. The goal is that this all be scalable, because I have 10 million individuals. Another goal is that this be spatially varying, because you can imagine that probability of voting for the Democrat, given your demographic characteristics, is different in the northeast of the United States than in the southwest, for example. And also, I just care about spatial statistics, so I like doing things that have spatial components. It was also just an excuse to do that, to be perfectly honest. And how do we do it? Well, using these machine learning methods that you may or may not want to hear about in detail, but just so you've heard there's names, Gaussian processes and kernel methods. And kernel methods are the same thing as support vector machines, if you've heard of that. Okay, so here is a little more notation, but this is the same thing I have here. So I've got n, little n, different bags, different electoral districts. I've got capital N1 individuals in the first one, capital N2 individuals in the second one, up to capital NN individuals. And so this is from the census, right? So within the census, I'm going to take everyone, not everyone, right? I'll throw out anyone who's under 18 because they can't vote. I'll throw out non-citizens because they can't vote. But everyone who might be a voter, foreshadowing, this is a problem, right? And then what's y? Y is a real value. Actually, it's a binomial count. It says number of votes for the Democrat out of the total number of votes. And what do I want to do, very generically? This is in one slide also just what is machine learning? I want to learn some function that goes from inputs to outputs. So regression might work if we had a way of dealing with varying size inputs, sort of linear regression, logistic regression, binomial regression. Some other fancy non-parametric method, neural networks might work, but we need a way of dealing with this non-standard bit, right? So once I've done that, I'll tell you how I do that in a second. The final step is easy. I want to make a prediction for just, let's say that these colors aren't actually the outcomes. Let's say these colors are women in red and men in black. Once I've fit my function f, I want to make a prediction about women. So all I need to do is take that function that I fit, f hat, and feed in just the observations of women, and that will give me the prediction I care about, support for the Democrat among women. Okay, I'm not going to talk about this slide. I can come back to this slide. I want to show you a picture instead. Here's a picture. Wrong picture. Here's a picture. Okay, so I told you I'd say it 3 times. So percent vote for Obama. This is just a picture, an illustration, right? I'm not doing things in 2 dimensions. I'm doing things in high dimensions. But imagine that the outcome, that's really in 1 dimension, is percent vote for Obama. So here is observed Y1. So this is a place where people did not support him. So let's say Texas. Y3, that's a swing state right in the middle, Pennsylvania. Y2, that's a Democratic state, Massachusetts. And then what are the predictors? Well, here's mu1. This is a high dimensional vector, but just one vector that encodes all of those observations. So mu is suggestive of it being the mean, but it's not just the linear mean of all those observations. It is mean in a high dimensional space itself. And I can give you more details on that if you care about them, but this is the high level idea that you need. So I've got my predictors mu1, which are a nonlinear function of the people who I have in, what did I say this was? Texas. And again, I've got women in purple and men in orange. And here's region 2, Pennsylvania, women in purple, men in orange. I take these covariate vectors, which are each of them is high dimensional, and I turn them into this mean embedding. That's the language of this kernel thing in machine learning, reproducing kernel Hilbert spaces, Mercer kernels. You do not need to know the details of this. I'll actually show you this in a much simpler way. But somehow I take these vectors, I turn them into this high dimensional vector, so it's a high dimensional vector, and then there is this label, help me, outcome variable. Same thing for region 3. And then once I have learned this function, which suggestively looks like logistic regression, I want to make a prediction. Well, here's my prediction for women, right? I do the same encoding. I use the same function. I get a prediction, question mark, because we don't know what was Obama's support among women. Same thing for men.
So the mu vector, does it have any interpolation which you can use?
Yeah, okay, so now let me go back and give you some interpretation of that. I don't have a picture. Okay, wait, do I have a picture? Nope, okay, so let me give you an interpretation. So wait, have people seen support vector machines? Is this something you've ever been exposed to? One person. Anyone else? Anyone else? 3, 4, 5. Okay. Okay, so I will tell you about support vector machines. So here is a classic problem in pattern recognition, which is like an old-fashioned name for machine learning. I want to build a classifier that will distinguish between circles and stars. The large margin principle says that I should put down a line, a decision boundary, that separates those two classes. That is not the same decision boundary that you would get from logistic regression, because logistic regression does not use the large margin principle. If you've ever heard of the problem of perfect separability in logistic regression, what that means is that when things are perfectly separable like this, the logistic regression actually explodes. There is no maximum likelihood solution, and that's no good. You can solve that in other ways. Because support vector machines, or in general just large margin classifiers, are just looking for a decision boundary like this, all you need is to have something that's got a large margin, meaning distance to the points. Okay, that's a great idea. It works very well, except what if the margin isn't a linear margin, right? What if the margin actually has to look like this? Well, if you think about your points living here in two-dimensional space, here they're still in two-dimensional space. If you think about some transformation of the points, and so probably you're used to doing straightforward functional transformations like taking x and transforming it to the log of x, taking x2 and transforming it to x2 squared, right? Those are simple functional transformations. You got it? You can generalize that to a much larger class of transformations, which are things like this, but also involve inner products between them. So x1 and x2 get transformed to that pair. And generically, for example, you might think, oh, x1 through xn, I'm going to transform it to all of the univariate ones, plus all of the inner products, plus all of the, well, inner products would also include squares, plus et cetera, et cetera, et cetera. And you might think, well, that's way too many features, covariates that I've now created, right? Everything's going to perfectly fit. The magic, why this is something that has been very, very, very successful in the last 30 years at this point in machine learning, is that you don't, A, have to actually represent this. This would fill up your computer memory. Or B, have to worry about overfitting, because built into it, and I won't talk about this, but built into it is some smoothness that says this can't be perfectly wiggly. There is some regularity that has to hold. So how does all of that work? All of that works with these transformations called kernels. A kernel takes something like x and some other input, y, and it tells you the similarity between x and that other input, y, which has an interpretation of representing that point x in a high-dimensional space. And so I'll just show you this very simple one. So here I told you this is the representation. Okay, so this is a vector x. So I'm going to say that k of x, what is the representation of it? So I'm just using this feature mapping, phi of x. It's just a vector that collects up those statistics that I told you about, x1, x2, xn, x1, x2, x1, x3, x1 squared. Okay. If you follow me so far, this next part is easier. If you haven't, I had a function, I had a covariate x. X is in a couple dimensions, age, race, sex. And now I've turned it into something where I've put down a lot of interaction terms and squared things. And now I'm going to summarize my bag of observations, right? Here's a bag, x1, x2, x3. I'm going to summarize that using just the sample mean. 1 over n for the number of observations, it's called ni, sum over I, and I'm going to use this function, phi of xi. Okay, let's pretend that we're just in one dimension. So we've just got x, and our function maps it to x and x squared. So what does this do? Well, it's actually very simple. It's 1 over however many observations we have, sum over I, a vector x, x squared. Okay, what's 1? Just write it up. 1 over n, sum over I, xi. That's just the sample mean. Everyone whose eyes have glazed over, wake back up. That's just the sample mean. 1 over n, sum over I, xi squared. That's just the second moment uncentered. So if I centered it, it would be like the variance. But it encodes the same amount of information as the variance. Okay, so this is not what we do. We do not use this transformation. We use one that's much higher dimensional. But it has the same effect. It captures the moments of the distribution. And if you capture all the moments of a distribution, then you uniquely characterize that distribution. So we never achieve any asymptotics because we never run this with infinitely much data. But you can prove that if you had infinite amounts of data, this would perfectly characterize any distribution using one high dimensional vector. And so that's the idea. So these observations get encoded in a high dimensional vector, which summarizes all of the moments. And here's another way to think about it, and then I'll stop talking about math. Here is a distribution you might be used to seeing, right? The distribution of income on a log scale. So how does it usually go? There's, some people at the top, and then there's a lot of people at the bottom, or something like that. I guess what it should be. Actually, I don't know what it looks like. Anyway, there's some distribution of income. You might think, okay, so for any district in the US, we have the observations of their income. Let's just summarize that by putting down deciles and saying what fraction of the people are in each of those. So what fraction of people make more than 90% over, let's use 90% for the entire population in the US, 80%, et cetera. And so now you're summarizing a distribution with just 10 numbers. So that would be a different way of summarizing distributions, and then you could run your regression using that. Okay, so that's the math that I wrote down before. I'm going to get a vector for each of my districts. And once I've got a vector, once I've just got real valued covariates, all the rest is just details of how I actually do my regression with my outcomes. So what I wrote down here is logistic regression with another level of nonlinearity, but you don't need that. It doesn't actually end up helping terribly much. So just think like, okay, I'm just going to do logistic regression. It's high dimensional, right? I have 2,000 predictors, and I only have 800 observations for the district, so it needs to be penalized logistic regression. So if I'm going to tell you one more great idea from computational statistics and machine learning, you've now heard about support vector machines. Do you all already know about lasso or ridge regression? Yeah? Yeah? Okay. If you don't, maximum likelihood estimation and ordinary least squares, while great, has many problems. And basically always, and certainly if you have more predictors than data, p is larger than n, you need to do some type of regularization. And so all this is one way of doing that. We use lasso in the newer stuff, which is a different way of getting regularization. Okay, and then I already told you about this. We can just make predictions using our fit thing. And this SI, this is kind of neat. So this is the centroid of each of the tracks. So it's the spatial location. Think of it as latitude and longitude. And that's another predictor that's in there. I don't think you care about the kernel details or the algorithmic details. You do have to go through all of the data once, which is costly because there's 10 million rows, but that's it. You don't have to keep running with those 10 million rows because it compresses it down to 800. And here are the results. Pictorially, certainly you want to see some numbers to see whether or not this fit. But remember, here's the exit polling on top. Those are the 18 states in 2012. And each of these is just a patch of color, right? Because they only gave state representative data. Here's 2012 using our data for each of the 843 regions. I don't know what this is the outcome for. Oh, sorry. So this is among women and among men. And so from these color scales, it's pretty hard to tell what's going on, but I'll show you a scatter plot. But everyone understands sort of what it is that, at the highest level, the headline that we are able to do. We're able to make this at a smaller geographic scale for the entire country, filling in the missing data. Here's the scatter plot. So I don't know if those colors show up. OK, well, you can see the points. The y equals x line, perfectly fitting, would be here. Of course, now that I know more about exit polls, I'm OK with it not perfectly fitting, right? It's not really ground truth. And then how do we do uncertainty intervals? So the exit polls have a margin of error, which is huge. And so that's what's shown here. And then I haven't included, I also have confidence intervals for those. I'll show those in a minute. But anyway, we do something sensible. You can see that women supported Obama more than men. And you can see that here. So we have the 843 districts. In each one, we have a prediction for men. We have a prediction for women. And then this is the gender gap, meaning women minus men. And there are places where, at least according to our model, it's the other way around. But they're very rare. And maybe they're very weird. Or maybe we shouldn't believe that prediction. But I think overall, it's very sensible. And this matches the national. So we always check also against the national one, which you would hope you'd be able to recreate. And so this does match the national gender gap very well. OK, so what if we have smaller subgroups? So there's a lot of high-income people in terms of voters, but there's more low and medium-income people overall. And so in any particular district, there's only a small number of high-income people represented in the census population. So I think it's something like, how I define this, greater than 150,000 is only like 3% of the population. So as you can see, it's doing something sensible in terms of, well, the predictions are kind of far off here, although it's sort of a systematic bias, so maybe it's not horrible. But the uncertainty intervals that I get show that we're really far. And so that is reassuring in some sense. We're certainly well within the, in this setting, they are 95% posterior credible intervals in a Bayesian setting. And so that's reassuring that at least we're within it, and that they're larger when they should be, which is when we have less data about high-income people in a sense. OK, that was 2012. We did not have any exciting conclusions to make about the 2012 election. Now looking back, and there's been other reporting on this, I think what people missed and what the exit polls missed was that there were more whites voting for Obama than the exit polls showed, than people conventionally believed. That's based on voter rolls data, where usually you are able to tell at least white versus black. I have not gone back to see what I have to say about that question, but it is an interesting and relevant one. OK, so now we came to 2016. We were working on this in September and October of last year. And we had this issue, which was one I kept foreshadowing, right? We're not modeling the right thing. We're treating everyone as a potential voter, and we're looking at vote outcomes. We're treating everyone as a voter, not a potential voter, right? So it's sort of amazing that we weren't farther off, because non-voting in the US, abstention, as they call it in other places, is a huge thing, right? American elections have, I don't know what, like 55% participation in US? Like, it's low. It's a lot of people who didn't vote. And there are significant third-party votes. So what we decided to do was to just put that into the model. So now we have, as an outcome vector, no longer a binomial proportion, no longer 55 out of 100 for Obama. We have the number of Clinton votes, the number of Trump votes, and OK, I guess we really should have four-dimensional. Clinton, Trump, third party, did not vote, but we put these together. So that could certainly be refined. There's nothing about these methods that say 3 works before it doesn't, but that's how we did it on election night. So how do we fit that likelihood? Well, maybe you've already know about this. There's generalizations of logistic regression to higher dimensions. Multinomial regression has other names, but that's what we use. Details about features and stuff. We wanted things to be a little more interpretable. One of the problems with all of this is that there's very little. There's like the definition of a black box model. And so we wanted things where we had some chance of being able to say this feature is more important than this feature. And this was a bit of a hack. This is a bit questionable. So we have some amount of data, which is exit polling data, which we do believe to some extent. That data could help us not answer the questions totally, but could help calibrate, could help keep things within reasonable bounds. And so in the end, we decided to include some amount, not very much, of exit polling data at the state level. And so remember, everything else is at these regional levels, district levels, but then we have a few extra bags that are labeled. So sets of observations, meaning the state set of observations, and the labels from the exit polls. But I have gone back and tried not using that, and sort of, it helps, because there's so many parameters here to fit, it helps sort of stabilize things. That's what I'll say. Okay, so what are some results? So again, you can see gender gap here, and there are some interesting outliers. Here are places where the support among women minus men exceeded 20% gender gap, which is kind of crazy, if you believe it. And there are places that go the other way, although not very many of them, where men supported Trump more than Clinton. That's what these are. The other sort of strange thing about the American system and about analyzing all this data, right? And sort of Simpson's paradox, but not really, right? Clinton won the popular vote. So anytime you're looking at these things, trying to think like, well, where did Trump's support come from? Trump didn't win the popular vote. So it's sort of a strange thing to actually think about. But anyway, here's what we can see. So among men, there's just top line number for the whole country. Support for Clinton was 45%, support for Trump was 55%. And then, so this is fraction of electorate for these two categories. So men were 47% of the electorate, women for 53% of the electorate. And so that's something that's interesting in its own right? That's something that you can get from exit polls if you believe them. You can get from voter files. Certainly, I would believe them from voter files. Voter files aren't available immediately and can be costly to obtain. And then participation rate. So this is just fraction of the electorate. And then this is saying, okay, well, there were three categories. There was Clinton, Trump, other. So you really should divide these two in half and say, okay, so men voted 22.5 for Clinton, whatever it would be, 27.5 for Trump, and 25% did not vote or voted for a third party. And so I think that that's also kind of a neat thing to be able to see. Exit polls, of course, can't do that, right? Because the exit poll is just of who's there, but it matters. There are a lot of people who did not vote. Half of men, 47% of women. Here it is by age. So you can see the obvious age breakdowns that you expect. Higher support for Clinton among younger people. Higher participation among older people. This seems pretty questionable. I don't have uncertainty intervals here. We fit it with a penalized frequentist method, which has some ways of getting uncertainty intervals, but they're nowhere near as straightforward. And so that is a failing of these new approaches. And here are some less likely things that you can use because they're in the census, right? So among people for whom a language other than English is spoken at home, our method says that Clinton has 74% support, but low participation among those people. Among people who, in wherever they're living, they lived there 1 year ago, so they have not moved recently. Trump had more support. Among people who had moved within the last year, Clinton had more support. Oh, sorry, moved here from outside US and Puerto Rico. Okay, so immigrants. Moved here from inside, so moved recently, still more support for Clinton. Active duty military, more support for Trump. Not enrolled in school, more support for Trump. Enrolled in school, a lot more support for Clinton, and so on. And so we have more and more tables, like large tables of this in the paper, which, by the way, is on archive, just a preprint.
Are all your results as difficult as these?
No. I wish. Where do we have really weird things? Maybe this slide will even have weird things. No. No. Certainly. You can go easily pick out, I picked out things that I could explain and that looked reasonable, and also things where there was more data for it. Some of the really kooky things are also just things where there's only a few of those people in any district. We don't have a great way of dealing with uncertainty insofar as estimating the mean embedding. So that's based on however many points there are in a district, right? So maybe there's 1,000 people who live in that district. That gives us a good estimate of the mean embedding. But then if you go to some unlikely subset, so if you take already interaction terms, so women who make more than 100,000, so that's going to be a smaller group in any. So then we ignore all of these. Then we're estimating a mean with very few samples. That's something that we can't estimate very precisely. There should be an uncertainty term that we propagate through. In this work, we don't know how to deal with that. I have a paper that will be on arXiv very soon, like later this week, where we do something fully Bayesian, where we take into account that uncertainty. And so that's future work. So here, this shows that you can do interactions, and that's, I think, where things get really interesting, because if you're thinking about the narrative, which we want to interrogate, we don't want to accept necessarily, but we want to think about men, we want to think about people in the upper Midwest, we want to think about less educated people, or not. There's some big questions about education and interactions with other things. Then those are things that typically you can't do with the exit polls, because there just isn't enough data in your sample, but we can try to do them. Okay, so this was fun and out of time, right? Yeah, you guys should ask me questions. We started late. Okay, so this was a more exploratory analysis, and it's a little unclear how to really describe what this is. The whole time I've been saying, I'm solving the ecological inference problem. Now I'm saying, well, wait a second. In and of itself, doing a regression on an ecological variable, you shouldn't give that the interpretation of, amongst those people, this is how they voted. But it's still an interesting thing to look at patterns, and that's really what people are doing when they're analyzing Brexit. They're saying, in locations in which there is this variable percent of people with college education, here is how the voting outcome went. And so as an exploratory analysis, we took a bunch of variables. For example, in the US Census, there is a variable called class of worker, which is a big categorical variable with like 200 different categories. And we said, okay, let's look at those 200 categories. For each district, we're going to do this nonlinear embedding, so we're not just taking the average, which, well, actually would make sense for categorical variables, so I'm not going to make fun of that. But if it was age, you'd want the whole distribution of age. And then I'm going to look at that, and I'm going to say, the outcome that I care about, in this case, vote for Trump versus vote for Clinton, how much predictive power does that give me? And so that's how you should interpret this. So just looking at the racial coding in the census, the fraction of deviates explained as compared to a null model is 86% from that race coding. And so race has white, black, Asian. It does not have Hispanic. That's counted as an ethnicity in the US Census. So that explains a lot of the variation. That's just by itself, there's an exploratory analysis. That doesn't say that that tells you, and I'm on the next slide, I'm going to show you plots that you might interpret as, oh, among blacks, here was the vote outcome. No, now I'm doing something that really is actually embracing this idea of ecological inference. And so this is listed by most important variable in explaining things. So 86 is really high, immediately jumps down to 74%. Ethnicity interacted with degree. So, you know, I was saying that I cherry picked, but this is the list. I didn't cherry pick anything here. Like I went through all the variables, and then I'm showing you the top 25 out of 100 variables. So ethnicity interacted with degree. That does match the narrative that people have said in terms of explaining variation. Of course, the question is, would it also have worked for Obama in 2012? Maybe, maybe not. And that, you know, there is this shift that we really, really need to go back and look at who are the voters who shifted from Obama to Trump. Schooling attainment, there you go, just almost as high as ethnicity. Detailed ancestry is cool. I'll show you that in a second. Occupation I mentioned, class of worker, a different coding of detailed ancestry. Okay, so maybe we can clean up the data and not do both of those. Industry coding, another way of coding race. Age interacted with usual hours worked per week, so there might be people who are in partial employment, I don't really know. Sex interacted with ethnicity, and so on. Okay, so here is a plot. So you should not interpret this plot as among men, here's the outcome. You should interpret this as a plot thinking about the explanatory power of this variable as a categorical variable at the level of the districts. So I don't have a short way of saying that. I think it's a slightly confusing idea, but the results are still very interesting. So among the detailed ancestry, categorical variable, coding in the census, looking at districts where people said that their detailed ancestry was white, which is in some sense a crazy thing to say. But anyway, those people did not say German or Italian or Mexican or, okay, Americans, also kind of a crazy thing to say. These are not people who I think are indigenous peoples. I think these are also people who would call themselves white if they had gotten to that part of the form. Those people, the support in those districts was almost 100% for Trump. But then there's this very interesting thing. So that's that axis, Clinton, Trump. This is participation rate. So among people, among places where people said white, the coefficient that was estimated was very low in terms of actual participation. So right, it's actually we're predicting a three-dimensional vector. Clinton, Trump, other, including not vote. And so this was, that point down there was something like 0.05, 0.05, 0.9. And then you can see reasonable things over here. So among places where African American lives, estimating the coefficient gave us more support for Clinton than for Trump, and sort of reasonably high participation. Here is interacting race with degree. I think I said that that one had high support. Here are some things that probably should have been left out. So Amerindian does mean indigenous people, and there just isn't that much data, right? So it's like, I don't know what's going on with that, but it probably shouldn't be on the plot at all because there's so little data. But here you can see totally reasonable things. White, no degree, being much closer to Trump, and being somewhere above 50% for participation, which I don't think is true, but you shouldn't think of it as what was the actual participation rate among white, no degree. It's participation rate in those regions. White, college degree being much higher percent participation and much closer to Clinton. Yeah?
The size of the circle, does that reflect the size of the population?
Sample size, yeah. And so, yeah, so I think probably we should just get rid of things that are below a certain size. And this, we already had to do some sort of nonlinear scaling just so that this didn't like take over the whole plot. And so these are really small. Okay, so just to sum up, I think that we have nice empirical results, but I think that there's much more to do in terms of actually, we would not be able to publish this in a poli-sci journal. We have replication code for these experiments in a package, and we have code just for dealing with the census data, which is in and of itself quite a challenge. My collaborator, Dougal Sutherland, is at UCL. I said next steps are a fully Bayesian model, but we actually have that. It's almost written up, and it will soon be posted on archive. Not for the election data, we do some synthetic data, but that's also useful. One of the questions that I didn't address at all was, have you even run some simulations to see if this works? And in that setting, we are running simulations and showing that things really are reasonable. We even get this thing that you would like from a Bayesian model, which is that the uncertainty intervals make sense. And so we claim 80% coverage, and we really get 80% coverage of our uncertainty intervals. And here are some future work ideas that I have. Maybe you have more. Told you about the fully Bayesian method. I have this idea that if you're actually doing a survey, sometimes it would be useful to, or if you're just doing some regression where you actually have the outcome variable you care about and you have predictors, it might be useful to also include a variable which is an ecological variable, a variable that encodes not just your covariates, but the covariates of the region that you live in. And so the example that I have from James Tilley, who's not here, is they're working on Ireland data, Northern Ireland data, I guess both. Northern Ireland data I'm thinking of. So the percentage of people living in the region who are Catholic versus Protestant, that's an interesting variable that you might include. And that is in some sense an ecological variable. And encoding that is very simple. You just encode that as 60%. But if you're thinking about distribution, maybe the age distribution of a region, or the number of immigrants, but in some more richly defined way. I think that would be a very interesting variable to try to be able to include in regression specifications. And I think that the work that I'm doing points at a way to do that, although we have not actually done it yet. And then just in terms of what's this actually useful for, it's useful for drawing these cool plots. It's useful for, in almost real time, we ran this the day after the election, getting some interesting results. But sort of stepping back, what it's really useful for, where this could actually be used, in my opinion, is A, in settings like Brexit, where we don't have any other source of data, or high quality data, and B, in places where we need to get from the data that we have, which is high quality but limited. So the voter file, I already said, is missing things like race and education. So we need to impute that. This gives, or could give, a way of imputing those missing variables for the purposes of then doing survey weighting or adjusting polls. And so one of the things that people thought went wrong with the state level polls in the US is that they didn't adjust for education. Okay, that's it. Thank you so much. Questions? I'm calling on you. Yes.
So, Seth, thank you very much. That was really, really interesting. So just nothing too technical, some general questions about the method and some thoughts. So one of the things that would be interesting from a political science perspective is your ability to predict. I mean, ultimately it's a prediction model, but you're very constrained by at the moment, I mean, given that you're using considered actually moving this towards a more pure prediction model, either based on election results temporarily, so over time, I don't know how feasible that would be, or else, as a consequence, or else using some type of polling data as libs. I know if you have issues with exit polls, you probably have more issues with most standard polls. And the second thing is, I mean, another thing that would strike me, which I think would also perhaps be important, is partisanship. So you don't actually mention this at all really in the models itself. And I mean, from a political science perspective, we know we have this data at the ecological level, if you will. So we have it at the macro level. We know what the percentage of certain partisans are across different districts. And this, I think, would also be. I mean, I just wonder what you're thinking of this. And then just the third point. I mean, I could see how the NHS would have to. I mean, this is amazing, right? So you could use this if we have ecological data on things like so cancer rates or certain types of illnesses by district. I mean, this is amazing because you can actually develop some type of risk profile on certain types of demographics. And I think I don't know whether you consider doing this.
Thank you for all the questions. Let's see if I can remember them all. So for the prediction one, I think this is a great question. I think that at the moment, the state of the art for prediction is models that have sort of been popularized, although you don't know the details from people like Nate Silver, 538, but there is a public domain one that was a French sociologist, I don't know his name offhand, that was sort of right before the end of the election, and you can see all the details, all the code was available online. It doesn't look at anything at the individual level in terms of the survey, and that's the next step, right? That's what you need to do. Right now they're just doing poll aggregation, they're doing it in a sophisticated Bayesian averaging way, but they're just taking top level for the state of Illinois. Here was the result. But those polls are of 200 people. Those 200 people have demographics. And so that is exactly where this should go in work that is sort of totally different. Gets to your third question about public health. I've worked a little bit, and there are other people who have done a little bit on combining health surveys, where you have a health survey of a country, a health survey of another country. Each of those surveys has individual level data, and you want to use that individual level data because you really care about, and in fact we actually cared about distributional outcomes. We cared about what percentage of the population had some disease, something like that. So it really mattered to use the individual level data. And so yeah, I think that all the pieces are there, whether you can do it scalably, whether you can really put it together and have it work. Partisanship was one of the things that they still don't adjust for, and this is something that I have followed these debates a little bit, but I don't know that I quite understand them. But if anyone's interested, I can find you a bunch of blog posts going back and forth about this right before and right after the election about whether or not the polls should be adjusted for partisanship. So I think the answer, in some sense, is yes. If you're doing pure prediction, then you should adjust for anything you can. If you have a good measure of it, and it changes over time, but you have opinion polls of it. So I had not thought about this at all, but yes, it might be possible to say, okay, I have some time varying measure of partisanship from opinion polls or whatever, and then I have my census data, which is not time varying. In some sense, it's time varying, but that really reflects like enthusiasm. More people will say they're a Republican if the Republican seems likely to win and is someone who's in the news a lot for good things or whatever. But it does change without maybe the underlying thing changing. And yeah, so I think it would be fascinating to try to use that as the outcome variable and to then predict it. I hadn't thought about it at all. Thank you for that suggestion. And then yeah, the NHS one is interesting. I will just say that I hope to do more on that in the future. Which is true, because I'm going to be collaborating with people who do public health at Imperial, where they have the actual microdata in this, very secure place, and so that would be how you can see whether or not what you're doing was right, and then you can do it for things where you just don't even have the microdata. Other questions?
You said you were using some off-the-shelf tools to do that. Can you say a little bit about what kind of off-the-shelf tools?
Sure.
Out here is scikit-learn or
Sure, yeah. So the
Python libraries with
here's a list. Python libraries, we did everything. At some point we were using MATLAB, and at some point we were using R, which makes it annoying to reproduce all of our results because you need to be able to run all these things. But yeah, so there's great stuff within scikits. And then actually we wrote a Python package that handles the American Community Survey. So if that's of interest, then It's a great place to look.
Would that be available for anyone to?
Yeah, so this is already on GitHub. Well, you'll have to get the link from my website, but on GitHub there is a Python package. It's based on scikit-learn. It does these feature representations for the American Community Survey. So it's a pretty specialized thing, but pretty amazing that I think my collaborator made this code available, and it's good code. I wrote the original stuff in MATLAB and using a Gaussian process package, and it was nowhere near as clean, and then he re-implemented things, which was great. And then this is the one, maybe, people here are actually using R, yeah? Yeah. So this is the place that you might already know about these things, but there are great packages for doing lasso and ridge regression, and those packages are called, I think, glmnet. Anyone know? I think glmnet, because it has some funny name, the elastic net for generalized linear modeling. But this is amazing. If you already know how to run a linear regression, or in fact any logistic regression, multinomial regression in R, and then you think, how am I going to do it when I have 2 million data points and 20,000 predictors? This package, same interface, you can do it. And that's kind of amazing. Okay. Well, oh, yeah. Ah, yeah, so the Bayesian stuff, depending on the talk, that's like all I talk about. There's 3 places you want to be Bayesian, maybe 4. X goes to phi of x. That has some parameters which you don't want to fix. You want to learn them, and I want to learn them in a Bayesian way, but I will often settle for learning them in a non-Bayesian way by optimizing something. So this has parameters lambda. I would like to have a prior over lambda. Okay, now I've got this, and I have that for x1 through x10, which all are in the same bag. And then I combine those all to some mean, mu, for bag 1. But that's wrong. There's uncertainty about this. So really I want to have a distribution over the mean. And so immediately I was motivated by these classic ideas of empirical Bayesian shrinkage estimation. So the name's Watson-Stein estimators. Anyway, there's a classic paper about estimating hitting rates in baseball. And the idea is if you have each player and they have some hitting rate, you could just use that as their estimate. Or you could do something that says, well, there's also the global estimate. I want to interpolate smoothly between each person's just frequentist estimate, just what is it? You know, they hit 5 out of 10 balls, and the global one, which is like no one gets above 6 out of 10. So I'm going to shrink everything a little bit towards the global mean, which is 2 out of 10. And you can prove in both a Bayesian and a frequentist sense that you do better by doing that. So by using more prior information. Okay, so that's the second place I want to be Bayesian. And then the last one is the obvious one, which we actually do, which is that I've got this function f hat that goes from my covariates and gives me predictions y. Well, I don't want to just have a point estimate for y. I want to have a posterior credible interval. I'll stick around for the coffee so you can ask me more questions there.
Okay. Well, thanks very much, Seth. Thanks for a very enjoyable and accessible